Hello and welcome to Lecture 4 of the Electric Potential Unit in PHYS 1201, and this lecture is all about capacitors. In an earlier lecture we talked about electrostatic equilibrium, which means that none of the charges in an object are moving. And remember that in a conductor the charges are free to move, and so if there was an E field inside it would cause charges inside to accelerate. But that means if a conductor is in electrostatic equilibrium, the E field everywhere inside must be zero, because otherwise the charges would accelerate and it wouldn't be in equilibrium. And we also were able to conclude, because of the charges not accelerating along the surface, that the E field everywhere on the surface is perpendicular. And furthermore, we could conclude that all of the charge in the conductor is on the surface, because if there was any charge inside, it would cause an E field in there. So that's what we know so far, but we can now add something else. We know that the E field strength is a slope of a potential versus position. And so note that if you follow any path inside here, the delta V along that path has to be zero, because that's what the electric field is. And so that tells us that the potential is a constant everywhere inside a conductor in electrostatic equilibrium. Now we're going to look at one of the simplest circuits you can put together. Here's a battery. We'll later on draw these with a symbol, but for now I'm just going to draw pictures of batteries. And it's in a circuit where we've connected the positive terminal to one side of a capacitor and the negative terminal to the other side. And it's all been connected for a while. So remember, we talked about this in an earlier lecture. Electrons would be pulled off of this plate and pushed onto this plate, and eventually there's a big charge on here and the current stops flowing. So there's no current flowing, and we know there's some potential difference, some voltage across this battery. And now what we're going to do is we're going to imagine that we're tiny, tiny little people and we can walk around inside the wires. So we're going to take a trip. We're going to start at point A, and we're going to walk around inside the wire, and here we're going to have to leap from one plate to the other to avoid falling. And we're going to continue until we come back to point A here, and we're going to write our distance traveled around as S. And we're going to graph the potential versus our distance walked inside the circuit. And so point A is here where we start, and at some point we'll walk through B, and then C, and then D, and we'll eventually get back to point A. So what happens? Well, we know that the potential is zero wherever we say it is. And I'm going to say we've made no decision, and so the potential here is just some arbitrary value, like so. So there's the potential where we start. And now we walk this way, and we arrive at the negative terminal of the battery. And as we walk through the battery, we're going to go through this potential difference. And the higher potential side of the battery is its positive terminal. So as we walk through the battery, we see the potential rise. So there's the battery. And now we continue walking, but look, we're in a wire. And all the way here in this wire from the battery to this side of the capacitor, we're in a conductor, and there's no current flowing. So this is a conductor in electrostatic equilibrium, and that means the potential is constant everywhere in here until we get to the capacitor. And now we're going to have to leap across here, and we know there's going to be a potential difference across the battery. Well, how big is it going to be? Remember that potential only depends on position. So we know when we get back to point A over here, we have to have arrived back at the same potential, because it can't have two values. The potential has to have one value there. Well, so we have to get back to that value of the potential, and it can't change in these wires because that's another conductor in electrostatic equilibrium. And so the whole drop back to what the original potential was when we left A has to occur in the capacitor. And so what that's just shown us is that the voltage across the battery has to be the same as the voltage across the capacitor. Another important thing about our capacitor connected to a battery, we know from a previous lecture that the voltage across the capacitor is directly connected to the charge on the capacitor and various properties of the capacitor. Let's just think for a moment what happens if we carefully, using, say, something that's insulated so nothing flows out of the contact points, and we disconnect the battery. Well, remember, these charges are here, and if we've used, say, rubber gloves to remove these connections so no charge could flow out through us, then this charge is trapped here. And so even though we've disconnected it from the battery, there's still this charge on the plates. It can't go anywhere, and so there's still a potential difference across the battery, or across the capacitor, even though it's no longer connected to the battery. Now let's think about what happens if we swap this battery out for a different one. So we put a different battery in here. It has a different voltage across it. Well, all the same arguments have to apply, and so the voltage across the capacitor has to change to match the one across the battery. And so what will have changed over here? Well, notice the distance between the plates won't have changed, and the area of the plates won't have changed. And epsilon naught is a universal constant. It certainly won't have changed. So all of those things are fixed for the capacitor, right? When the capacitor arrived from the factory in the bag, it had all of those things fixed. Those are properties of the capacitor itself. And so when we change the voltage across the capacitor, they don't change. What's going to change is the charge on the plates. So we could say this is a variable under our control, and we control it by changing the voltage. And so it makes sense to rewrite this a little bit, just to collect all the things that are constant for the capacitor out front, and stick the thing that's under our control here. And in fact, we usually flip that around, so we would write it Q is epsilon naught A over D delta V C. And so all of this is a constant property of the capacitor. And since it's an unchanging property of the capacitor, we might as well just assign it a name. It's called the capacitance, C. So any capacitor is characterized by its capacitance. And look at the units of it. We know we can write this Q equals C delta VC. And so this is in coulombs, confusingly using C, just like this C. This C is coulombs, this C is standing for capacitance. This is in volts. And so the capacitance has to be in coulombs per volt if that equation is going to work. And so the units of capacitance are farads, F, which is coulombs per volt. And so if you think about what that means, it's telling you per unit of voltage applied across the capacitor how much charge gets stored on its plates. Let's now think about how much energy we store in a capacitor when we charge it. So here's an uncharged capacitor. We're connecting it to the battery, but here's a switch. And this is terminology you may not know. The switch is open. And what we mean when we say it's open is that there's a break in the circuit here. But now we're going to close the switch. So as soon as the switch is closed, charge can flow. And so now, remember, electrons are going to leave here and come around to here. So we're going to start seeing a buildup of charge. But this happens very, very quickly. But we're going to think about it and the process. And I'm going to plot delta V on the capacitor versus time. And it's going to rise. It starts at 0 because there's no charge, and the charge is proportional to the delta V. But as the charge builds up, the delta V builds up. It turns out the curve looks something like this. We're not going to worry about that, though. The only important thing here is that delta V is increasing as the charge increases. And so eventually, we wind up with the full whatever final charge Q we have on the plates. And now let's think about the amount of energy stored. Now, naively, you could say, oh, well, we know that that's related to a delta V like this. Q times delta V gives us a delta U. But wait, the first bits of charge you moved around here, you moved through only a very small delta V. Later charges that you moved through here, you moved through a larger delta V. And so not all of this total charge Q moved through the same delta V. And so one way of thinking about it is that on average, the charge is moved through some average delta V. And a good guess for what that average would be, which turns out to be correct, is that it is half of the final delta VC that you wind up with on the capacitor. Now we have just one more step. Let's take this identity for Q and let's substitute it in there. So we get C delta V on the capacitor, a half delta VC. And so as a final expression for the potential energy stored in a capacitor is just a half C delta VC squared. Let's just think about how this works out for numbers in a typical capacitor. And I've done the calculation because it's simple. Pull apart a typical capacitor. Remember, it looks like this. You're going to find the plates are around that big. Pretty typically, there's a lot of variation. The distance between the plates is the thickness of a piece of paper. And we're going to ignore the effect of the dielectric other than that it holds the plates apart. And then if it's connected to a 1.5 volt battery, right? A standard AA cell or a D cell, they're both 1.5 volts. The difference between them is the amount of energy stored inside. I'll leave you to guess what the voltage is on a 9 volt battery. It's a lot like the year that the War of 1812 started in. Anyway, if you just pull out the capacitance here and calculate it, just order of magnitude, right? 10 to the negative 12, 10 to the negative 15, 10 to the negative 11, maybe another 10 out of this. You get about 10 to the negative 10 farads. Let's check the units because it's good practice, right? Coulombs squared per Newton meter squared times meter squared all over meters. The meters squared are gone. You get coulombs squared per Newton meter. A Newton meter is a joule. And a joule per coulomb is a volt, and so that's farads. So picofarads is fairly typical. Of course, you can find much bigger capacitors. If you now just plug that into the delta U, you're going to get about 10 to the negative 10 times 1.5 squared is really still of order 1. And so you get values of about 10 to the negative 10 joules, not much.